So here's a little lesson on the physics of gardening. When you use your pruning shears, all you're trying to do is create stress in the form of a shear force, and you want the resulting strain to be so great that you reach the fracture point and end up cutting whatever you're trying to trim back or prune. So this is all consistent with the study in our previous lessons on stress to strain ratio, and in particular we'll focus on the behavior of shear forces for objects that are stressed within their proportional limit. So let's review some expressions for the ratio of stress to strain for materials with elastic behavior. So we talked about bones and guitar strings. A guitar string would be like this example, an object that's under a tensile stress and has a resulting strain measured as an elongation of the material, whereas a bone will approach fracture as it's compressed. So a compressive stress leads to a reduction in the length. But either way, there's some fractional change in length in both of these cases. So in both the guitar string or the bone or anything that's under tension or compression, there's a constant of proportionality that describes the slope of this graph. And that constant of proportionality is known as Young's modulus. And Young's modulus is calculated as a ratio of stress over strain. Here, the stress isn't just the amount of force, it's the force per unit area. So we see a cross-sectional area has been labeled in both these diagrams. And the resulting strain is not just how much the length changed, but it's a percentage change in the length found by calculating the change in length divided by the initial length. So there you have it. There's Young's modulus. Then we also learned about bulk modulus. If a three-dimensional object is squeezed inward at all sides, then there's an absolute pressure acting on the material. But we're more interested in what we call the gauge pressure, or just the increase in pressure. So here we have a stress to strain ratio. The stress is just the additional pressure, and the strain is the change in volume divided by the initial volume, and we refer to that as the bulk modulus for this material. So now we want to study the shear modulus for materials. So if something is forced so that it's pushed to the right at its top and pulled to the left at the bottom, and here we're using the left edge as our reference point, so it's as if the object is anchored from this point, then by having these differences in force that don't align through the center of mass of the object, there's a displacement x for the top part of the object compared to the bottom part. And then the object also, we'll say, had some initial height to it. So here we're going to measure our stress as, again, force per unit area. In this case, it's the force per unit cross-section measured this way for the material, right? Here's our cross-sectional area that goes in this formula. So ratio of stress over strain. So the strain in this case is also going to be a fractional change. It's x, the horizontal displacement, divided by h, the height of the object. And we refer to this ratio of stress over strain as the shear modulus for the material. So pruning shears, I don't know if you've ever used those or not, if you do much gardening. We use the same language just for everyday household scissors. Scissors are often referred to as shears as well. Now, the value of h for a pair of scissors is really small, but there is some value of h. The one blade doesn't align exactly with the other blade, and any right-handed person who's ever grabbed a pair of left-hand scissors or vice versa is very aware of the fact that there's a value of h when you apply shear force using a pair of scissors. And so regardless of whether the value of h is big or not, as long as there's some value of h, we can express strain in this manner. So this is how we calculate shear modulus.